Good evening. Wow. Could I have you come in and have a seat, please? I'm Danny Wyndham, HudsonAlpha's COO, and I would like to welcome you to the last session of our community event series for 2024. And you're here on such a beautiful night. When I walked over from the main building, I swear I was looking for Ichabod Crane to come around the corner at any point. Over the past year, we have conducted 9 of these community events. The majority of them were free of charge. Through that, we have hosted over 4,300 attendees, all as part of our mission to provide educational opportunities in the field of genetics and genomics to lifelong learners just like you. Our featured speaker tonight has made significant contributions toward the understanding of the role of genetics as it relates to cancer. And as such, I would like to thank our sponsor for tonight, the Russell Hill Cancer Foundation. The team at Russell Hill has supported the work that's gone on at HudsonAlpha and has been very instrumental in helping our scientists advance our understanding of cancer, and we are very grateful for all that they have done. We're really in, thank you. We are all in for a treat tonight as we are honored to have Dr. Harold Varmus with us. Dr. Varmus is a Nobel laureate who has held numerous prestigious positions over his career, including Director of the National Institutes of Health, Director of the National Cancer Foundation, President and CEO of Memorial Sloan Kettering Cancer Center. We'll hear from Dr. Varmus in just a bit, following which our own Dr. Sarah Sharman, our Research Communications Manager at HudsonAlpha, will moderate a discussion between Dr. Varmus and Dr. Rick Myers, HudsonAlpha's Chief Scientific Officer. But first, I would like to introduce Dr. Daniel Schroeder. Dr. Schroeder knows firsthand the significant role the discovery of oncogenes has played in impacting our understanding of cancer and cancer research. He's a physician at Clearview Cancer Institute. He received his PhD and MD from the University of Alabama in Birmingham. We are really indeed very fortunate to have a cancer institute the caliber of CCI and physicians the caliber of the Schroeder family as oncologists in our very community here. So please welcome Dr. Daniel Schroeder to the stage.
Thank you, everybody. So my name is Daniel Schroeder, and I'm a medical oncologist here at Clearview Cancer Institute. And it's really exciting to have Dr. Harold Varmus here to talk about his research and career. And so before he does that, I just wanted to take a couple of moments to kind of illustrate to you all really just how important oncogene research has been in transforming how we actually take care of patients day to day. So when I think about different cancers that we treat, as I was thinking about this, it's actually really hard for me to think of any cancer that doesn't involve at least thinking about or testing and sometimes treating targeting cancer oncogenes. But I don't have, and you didn't come to see me, and I don't have all night, so I just wanted to just kind of paint a couple of examples. One is lung cancer, and the other is chronic myeloid leukemia. So first, lung cancer. I remember the first time I went in as a medical resident into a lung cancer clinic, and the first patient I saw, I was shocked because it was a male who was in his early 30s. He had never smoked, and he had stage 4 lung cancer. And I just thought, how could this happen? I was used to thinking that really it was smoking that would drive it all, but it turned out that he had a gene mutation called EGFR that had caused the development of that cancer. And targeting that mutation put his cancer into remission. And that was in my medical training, and so I've now gotten to see a lot of patients where we're able to target that EGFR mutation and help put their cancers into remission. And one in particular was a lady here. She got diagnosed when she was in her mid-50s, and at that time, the average amount of time people had to live with a stage 4 lung cancer diagnosis was 1 year. And that was not good enough for her, let me tell you. So she entered clinical trials targeting the EGFR mutation. Now these medicines are approved. And she battled. I got to come on a little bit later in her journey, and she lived over 12 years. She went from that average 1 to 12 years. She got to see her grandchildren being born, and it was just quality time, and that's what it's like living. Now that EGFR concept has really translated completely how we take care of lung cancer. In fact, anytime someone gets diagnosed nowadays, we look for, and the guidelines tell us we need to look for these oncogene mutations so that we know how to target them. And so most recently, I have had a patient, I'll call him Mr. P, who he was diagnosed with a different oncogene that while we were treating him, we weren't really able to target it. It was called KRAS. And we did his chemo treatments and immunotherapy treatments, and he did well for a while, but ultimately his cancer grew. But he would read, and he would stay on top of things, and he said, look, I know there's this drug coming out. It's not available yet, but it's coming. And so we were actually able to get access to that drug through a compassionate use access, and immediately, as soon as he took it, his cancer went back into remission. And he lived over 2 years with good disease control. And you know you're doing a good job as an oncologist when your patients call you and cancel their appointments. But because he went hang gliding, he went to 3 different continents, he traveled all the 50 states, all the time he's taking a pill. It's, some side effects, but really doing well. And it allowed him to accomplish a lot of life goals that honestly, I think a lot of us don't do, even if we think we have a lot of time. And he really taught me how to take advantage of time. And so just real quickly, I wanted to also talk about CML. Now, in just a few decades ago, if someone was diagnosed with chronic myeloid leukemia, the treatments mostly looked like high-dose chemotherapy and then trying to get him to a remission and do a stem cell transplant. And the outcomes just weren't very good. But then oncogene research led to targeted therapy that can take that leukemia and put it into remission and then many times cure it. And so just yesterday, I had a patient who's 22 years old, and he got diagnosed with CML, and I got to tell him yesterday that he was in remission. And he, with confidence, I can tell him that I think you're going to live a full, healthy life. And we wouldn't be able to do that in any way without oncogene research. So I just, again, wanted to take a couple of, yes, sir? All right. That's awesome. Thank you. So I just wanted to take just a couple of minutes to just paint those pictures. But now, next I'd like to ask Dr. Rick Myers up to introduce Dr. Varmus. Dr. Myers is the Chief Science Officer and the M.A. Loya Chair in Genomics and faculty investigator here at HudsonAlpha to introduce his colleague, Dr. Varmus.
Thank you, Daniel. And there are many, many stories like that. I just want to say how happy I am to have Harold Varmus come visit us. Harold, you may not have calculated this, but we've known each other for almost 40 years. And we were colleagues at UC San Francisco, where he was. And I just want to tell there were so many stories, very, very good stories about Harold. Somebody I've admired. He was kind of a mentor, but even because I was just starting my lab and he was already well established. And what happened about 7 or 8 years after I was there, Harold got tapped to run the National Institutes of Health, which is a huge, I think many of you know, but that we rely on that for biomedical research. Other agencies like National Science Foundation and many others, but NIH is the biggest one and really funds and you're going to hear some about this fund's research. That is, we have to figure out how things work if we're going to do anything about it, and we don't know how everything works. And so I just remember when Harold was tapped, he was running this amazing lab that was doing amazing work, and we were all sad because that meant he was going to go and stop. Well, we thought he might stop running his lab. It turned out he didn't. He took his lab with him to NIH in Washington or in Bethesda. But then it hit me and most of us, you want smart people like this running the big institutes like that. And man, oh man, the job that he did was, I still think he's the best director we've ever had, sorry. And then, as you heard, he did many things after that. Went to run Sloan Kettering Memorial Cancer Center in New York City. And then back then, he went back to NIH and ran the National Cancer Institute, which is by far the biggest of the 27 institutes at NIH, $6, $7, $8 billion a year budget, because cancer is one of our biggest killers. So I'm really happy to have him. We're going to try to have a little banter on the stage after he gives a talk, but has so many interesting things to say. And this is going to be not telling you details about oncogenes, he'll tell you, but also how science works, his history. There's been a lot of exciting things, and I was there when he won the Nobel Prize with this, not in the same room, but I got to watch on this with his colleague Mike Bishop. So Harold.
Well, Rick, thank you very much, and thank you to the audience for turning up on this foggy night to hear me chat. As you've heard, and I have faced this truth, Rick, we've known each other for 40 years. I've long wanted to come down and see what the hell is what's Rick doing down here in Huntsville? And finally got the chance this afternoon to meet with his colleagues and many of the trainees who work here. Had a very pleasurable chat with several people, a good lunch at your cafe, and most importantly, this was a chance for me to go with Rick and friends of his and my wife, who's here tonight, to see many of the important sites that reflect the fight for civil rights that went on here in Alabama, and about which I only knew through reading, and to be in the presence of places in Montgomery and Birmingham and Selma and other places that figured in the great civil rights enterprise of the last half century was extraordinarily moving for me, and I'm extremely grateful to all of you for bringing me here, giving me a chance to live this history. What Rick has told me that I should do from the podium is to prepare all of you to ask good questions, think about good questions, and have a discussion. So I've been asked to speak for roughly 15 minutes or so about my career in research, my views of how research is done. And I'm going to try to do that if I can I asked for a little more than 15 minutes, maybe 20. And what I will try to do in those moments are reflected in the slides. What I'd like to do is tell you a little bit about myself and how I came to become a scientist. And I'm going to sprinkle this account, which will include something about the oncogenes you have been hearing about, a little bit about how they were discovered, as well as some reflections on the notion of how science works, how it interacts with society, how and why it's important for the country to continue its efforts to make science an enterprise of which the United States and the rest of the world can be proud, how science works as an international endeavor, and hopefully provide the material that many of you will consider useful for thinking about questions that we might raise during the discussion. Having trouble getting these things to advance. I don't know why that is. There we go. So I'll talk a little bit about my own origins as an individual, not necessarily a scientist, a little bit about my own transit from being a public school student to becoming a scientist, an event that actually happened uncharacteristically late in my own personal development. I'll talk a little bit about being a scientist, which includes the kind of scientific work I did without getting into boring details, and what it means to oversee science, as you've heard I've done in at least 3 significant roles. And throughout all of these topics, I'll be referring to what I call axioms for doing science. When I speak to students and young faculty, I like to talk about the principles by which I myself have tried to live my life in science, and by which I hope others will live their lives in science. In addition, I'll be hopefully referring fairly frequently to the major mission of HudsonAlpha, namely how to make use of our knowledge of genomes, the repository of all information that provides a blueprint for how plants and animals and human beings too develop and function. And even though much of the work I tell you will be work done before the tools of genomics, the study of genomes, was highly refined, nevertheless, I hope you'll see that one of the exciting features of the life I've led in science is to understand how scientists have been able to move from a fairly primitive notion based on the principles of Darwin and Mendel and all these famous 19th century figures, was transformed by technological developments of the kind that are being nurtured here at HudsonAlpha and overseen by Rick and his colleagues. So, a major task to undertake in the remaining 15 minutes. I hope I won't go too fast. I'll try to be Southern, not Northern, and we'll see how it works. So, first, origins. I actually, although I portray myself as a Northerner, I spent formative years from ages 2 to 6 in Florida, when my father was a physician in the Air Force during World War II. A revelation of how old I really am. And then we moved back to Long Island. Now, Long Island's a place where my parents had located as youngsters. And my father was the son of 2 people who fled Poland in the early years of the 20th century because they were Jews and there was anti-Semitism rampant in Poland at the time. He came to America. He was born in America and lived the American dream. His father was very poor. His mother died in the influenza epidemic of 1918, and yet he was able to obtain a small scholarship from his community in Newark, New Jersey. Went to Harvard College for a couple of years until financial difficulties required him to leave. Went to medical school, became a practicing physician on Long Island. My mother was born to parents who had fled what we now would call the Ukraine, but was then called the Austrian-Hungarian Empire. She too was able to go to an Ivy League school, in this case Wellesley College, became a psychiatric social worker, and lived a comfortable life as my father's wife on Long Island. I went to public high school in this town, Freeport, New York, where I grew up after our time in Florida. Went off to Amherst College as a pre-med student, the obvious thing if you're the son of a Jewish physician on Long Island. But I quickly became seduced by other topics, especially English literature. Wrote a thesis on Charles Dickens, whose picture is shown here. And then went off to graduate school at Harvard University in English. But during graduate training, became concerned about the loss of any opportunity to exercise the part of my mind that had a quantitative scientific bent. Went off then to Columbia Medical School, trained in internal medicine. At that point, I was 28 years old, showed no particular tendency to do any science. But at that point, I did become a scientist. How did that happen? Well, a confluence of political and personal events allowed me to see the advantages exploiting a prolonged adolescence. 28 years old, no real prospect of becoming a scientist, but at that point, there were a difficult set of prospects ahead for people, for males who were graduates of medical school. You'll recall, some of you in reality, some from your reading of history, that we were engaged in the war in Vietnam, one to which I personally was deeply opposed, and many others were too, including, and many posters like this were found around the country. The Congress had instituted a plan called the Berry Plan, which required MDs who were newly minted and were male to either serve in the armed forces or do research or some kind of service in the public health service, which then, as now, included the Center for Disease Control, the Indian Health Service, and the NIH. And the alternatives were fairly unacceptable. So I joined a cohort of individuals who were privileged to work at the National Institutes of Health and to either exercise their research skills or, in my case, learn how to do research. You probably can't see me, but I'm the third from the right in the back row. You'll note that there's a rather dramatic gender imbalance here, representing both the difficulty women had in getting into and graduating from medical school and the low selection rate for women to serve as research staff at the NIH at that time. During my time at the NIH, I was assigned, not quite at random, but with very limited research experience. I wasn't great fodder for most of the distinguished people at NIH, but a very brand new investigator there thought I might have some potential, and he liked the fact that I knew English literature because his wife was a poet and needed someone to talk to at lab parties. My mentor, Ira Paston, who is happily still working at the NIH these many years later, had made a discovery that a very small molecule, a so-called second messenger molecule in mammalian cells, had the ability to control the ability of a gene in bacteria to make the protein that gene encoded. And the question was, how does this happen? And does it occur by increasing the production of RNA from the gene or from increased translation of the RNA to make protein, or because of stabilization of the RNA or the protein? And I set off to try to answer that question. Very difficult to measure because this is an era before gene sequencing and recombinant DNA technology and all these things that everybody, even laypersons, are familiar with. It was very difficult to measure how a single gene was working and responding to signals like cyclic AMP. But we did have some methodology, partly helped by some natural events that allowed genes to be transferred between cells in a natural way, and because of the ability to use some of the principles of the structure of DNA to ask two molecules to recognize each other and to measure the amount of one molecule using another that happened to be radioactive. And once I learned this technology, it was possible to answer a question, and then to think, I know the answer, I can ask more questions, and those questions might be interesting. And so those were big lessons that I learned in my 2 years at the NIH. And I learned that it was really important, except for sex, very few pleasures exceed having a really potent way to measure something specific. Secondly, this was a model in bacteria for studying how genes are controlled. Obviously, just about everybody in the audience has roughly 20,000 genes or so. They have to be regulated in many different cell types. How does that happen? This is a good model for trying to understand that. And then there's the exciting thing that when you go over a little hill, you see a lot more hills ahead of you, and that's exciting. You've answered something, you want to answer more things, and when you get an answer, you're excited. And then there's the question of gossip. We all like gossip, and when you can tell your results to friends, that's an exciting reason to go on and try to do more science. And after 2 years of doing this and writing up papers and being excited about research, I realized that while was fun to work with bacteria, there were bigger problems that I had learned as a medical student that were now ready for study or exploitation, if you will, using the techniques that were now coming on board to study biological problems in bacteria. And that included cancers, a disease I was interested in for personal reasons because I had watched my father trying to take care of patients who had cancer and didn't have the opportunities that were related, for example, in some of the stories that Daniel just told you. So that's where I decided I'm not just going to have this training period, do my duty to my country in the midst of a Vietnam War, and go back to being a physician. I was going to go try to become a scientist on my own. And I went out at that point to the University of California, San Francisco, to work with a man of similar age to myself, who was a few years ahead of me and had already gone through NIH and learned some of the things I had learned. And one of the things that was important to me at that point was choosing a question or a set of scientific questions that I thought would be an appropriate venue for a life in science. And the things that I realized and learned were important conditions for satisfaction of a life in science is the questions be inherently interesting, that they have long-range potential, and that they be feasible with technical tools that were already available. And there was the additional opportunity of thinking they might have real societal benefit in the long run. And I was fortunate in making a choice, having taken courses during my time at the NIH and learned about the viruses that were able to cause cancers in animals that had very small genomes. And as I've already mentioned, and as you all know, human genomes are very large with 3 billion base pairs and over 20,000 genes, whereas some of these viruses that cause cancer in animals had a few million base pairs, not billions, and had maybe 3 or 4 genes. And those small genomes might provide an opportunity for trying to understand how cancer actually arises and what you might do to confront cancer, prevent it, or treat it. In my large conception of how I might proceed, I realized there were 2 really big questions to try to grope with. One was to understand how those viruses grow. It was already known at the time that I entered this field that whereas you're all used to thinking about genetic information going from DNA to RNA to protein, that in the case of some of these viruses, the genome was composed of RNA. The RNA was converted, one might say, backwards into DNA and then read out as RNA and protein. That was inherently interesting and raised the question of how those viruses actually multiplied. And the other question was, how do these small viruses turn a normal cell into a cancer cell using very few genes? And 50 years later, now, we can also see the societal benefits that one might have dreamed about in 1970 when all these things were happening in my life, what we've learned from understanding how these viruses grow is how to treat HIV/AIDS with drugs against the enzymes that are required for the viruses to multiply. And secondly, as you heard from Daniel, as I'll mention in just a moment, we learned from studying these viruses about targeted therapies for many kinds of cancers. So I try to summarize this story briefly. As my colleague in San Francisco, Michael Bishop, about whom I'll say more in just a moment, and I focused on a virus that had been discovered in New York City in roughly 1910, a virus called Rous sarcoma virus. The Rous sarcoma virus, shown in the bottom line on this slide, had a very small genome, about roughly 4 genes, and the genes that encoded proteins and enzymes that are required to make a virus particle. And they had one additional gene that we call SARC that was required for the virus to make a tumor in a chicken or to change the behavior of cells that are grown in cell culture. Moreover, other scientists, including one important colleague, still with us today, named Peter Vogt, had shown that there were versions of this virus that had lost the viral Sark gene. There were deletion mutants, but they still had all the genes and all the genetic information required for the viruses to multiply. That was important too, because it was possible for us to derive molecular radioactive probes that encompassed only the information found in the transforming gene or the oncogene Sark, and to ask a very important question: where did that viral gene come from? And to show that, in fact, it was a slightly altered version of a normal cellular gene that by itself was actually necessary for normal development of animals like chickens and mice and human beings, and that somehow in the course of virus multiplication in chickens, that information was pulled out of the chicken genome and made into a gene that had the ability to cause a cancer when returned to chickens. Now, the significance of this was that that told us where viral oncogenes came from and gave us some insight into what kind of genes might be capable of turning a normal cell into a cancer cell. That notion became much more powerful when it was recognized by the work in our own lab and in many other labs that this was only one of many 20 or 30 other examples of viruses that contained a gene that could carry out the conversion of a normal cell to a cancer cell. And each of those turned out to be somewhat different from the next. Some belong to important classes of genes that I just don't have time to describe in detail. And many of those genes were not simply the precursors to the viral genes that cause cancer in infected animals, but were also mutated without any evidence of a virus infection in human cancer. So that made us then feel as a community that the discovery we had made that a viral oncogene was derived from a normal cellular gene, and that the genes that this class of viruses led us to recognize as precursors to the viral cancer genes were also the genes that could be mutated during the generation of a human cancer. And that was an important observation for the reasons you heard earlier from Daniel, namely that when those genes are mutated, it's possible to say they are the driving force in the development of a cancer, and that they might be points of attack for a targeted therapeutic approach to cancers. You heard about some of these examples from his brief dissertation about his own medical practice, and shown here are some of the examples that he alluded to. First, chronic myeloid leukemia, where a joining of one such precursor to a viral oncogene called ABL drives chronic myeloid leukemia and can be treated with a variety of drugs. Mutations that are found in a variety of cancers, but especially in breast cancer, a gene often referred to as HER2, can be treated with antibodies against that protein. There are a variety of genes, EGFR was the one he mentioned, that may be mutated in a variety of lung cancer called lung adenocarcinoma. And in patients with melanoma, about half the melanomas have mutations in a gene called BRAF. Now, I want to say a few other things about the nature of the social activity that goes on in doing this kind of work. First, although people often imagine research is being done by somewhat irregular individuals working in a white coat in a solitary room. In fact, cancer research and every other kind of research is a team sport, and you can see that displayed every day in the halls of this institution. In my own particular career, that was exemplified by an unusual long-term, nearly 20-year partnership that I had with my colleague Michael Bishop, who is shown with me here, was we ran a meeting at Cold Spring Harbor about a long time ago in the 1970s. The rest of our team, and a picture shown in 1985, a picture taken at the time that the two of us received the Nobel Prize in Medicine, and then a picture of us as captains of our softball teams after one such game was over. Unfortunately, a game in which Mike's team was victorious. As you've already heard from Rick, one of the things that the Nobel Prize meant to me was that suddenly people took my opinions seriously. And one of the things that resulted from my suddenly becoming more involved in making policy, national policy on how NIH is funded and how it conducts its business, is that I had some opportunities not simply to do science, but to oversee how it's done throughout the country. And in particular, I had 4 years after we received the Nobel Prize, I was named to be the director of the NIH. Here I am arriving on one of my first days at work on my bicycle in Bethesda, and moved from simply giving advice to actually being responsible for the kinds of things that others might criticize me for, and often did. What I learned in a very fundamental way is that people talk about science as being apolitical. That's just not so. Some of the work we do is apolitical, but science is an enterprise created by society and important as a way of serving society. And there are many pleasures with undertaking such a job. One, in my case, was that I lived at the NIH at a time when there was strong political support from both of our major parties for the scientific enterprise, a time when the budget of NIH was growing. In fact, it began to double before I left the NIH. It was a good environment for doing all the things that leaders like to do. And at HudsonAlpha or any other institution that does science, recruit great individuals, expand the facilities, construct new buildings, and to make achievements, which included carrying out the Human Genome Project, which has been so essential for science done here at HudsonAlpha and everywhere else, carrying our scientific mission into other parts of the world, building a way to share the results of science through a digital library called PubMed Central, through the ability to develop the kinds of cancer drugs that we've been talking about. And one of the achievements that occurred during my own time at the NIH was some of the first targeted therapies used especially in patients with chronic myeloid leukemia, developing new treatments for HIV that depended on our understanding of how RNA tumor viruses multiply, building the Vaccine Research Center, which turns out to have been so important in the recent COVID-19 pandemic. Also happened to be a good bike route to work, but we won't talk about that in any detail. Memorable moments of my time at the NIH included appearing with Tony Fauci, America's most famous scientist at the moment, talking with Bill Clinton and Al Gore about the need for a vaccine research center, applauding Bill Clinton with Hillary when the president announced the initiation of the doubling of the NIH budget in 1998. This led to other kinds of leadership and advisory activities, such as talking with President Obama, as I am here. I'm sitting on the right side of the table. President Obama is on the left, to talk about what people have largely now forgotten about in the wake of the COVID pandemic, about influenza viruses in 2010. I want to just point out something that probably is intuitively obvious to everybody. Science and scientists are devoted to understanding truths about the world, truths that apply everywhere. And science, in that sense, is inherently international, and importantly, is an activity that we engaged in the best of circumstances in a highly international fashion. My own lab, shown here, in Central Park when the famous Christo exhibit of the Gates was up in Central Park is highly international with people from all the indicated countries. This is true of, I'm sure, labs everywhere around the country. During my time as NIH director, we began to work with many African scientists on malaria. This is a picture showing me and the head of the Pasteur Institute from France in Dakar, Senegal, in a meeting that led eventually to the development of something called the Multinational Initiative on Malaria. Other efforts that NIH is involved with include malaria research in Bamako, Mali, cancer research in Uganda, the kinds of developments that led to President Bush's so-called PEPFAR program. It's happened to be topics of lectures that I gave about scientific diplomacy some years ago. Finally, just make one other point, and then we move on to the more general discussion. I think it's good to remind ourselves frequently that science is a way for us to inspire ourselves and others and to unite us and teach us what it is all about to be human beings. And one such inspiring moment of many was the discovery of the double helix, from which virtually everything I've mentioned and virtually everything done here in the HudsonAlpha Center is based, namely the recognition of the coding potential and double-stranded structure, double-stranded helical structure of DNA that was unveiled in an iconic moment in the history of science with Watson and Crick discovering what DNA looks like and how information can be encoded in DNA, giving rise to our advances against AIDS and cancer and many other diseases, and the kinds of things that we celebrate by coming together here under the auspices of HudsonAlpha, which is something I'm proud to do tonight. Thank you very much.
Thank you so much for that wonderful talk, Dr. Varmus. As Danny mentioned, my name is Dr. Sarah Sharman, and I'm so excited to moderate a discussion now with Dr. Varmus and Dr. Myers. So it's not every day you meet a Nobel laureate, although, Harold, I have to tell you, you're my second Nobel laureate I've ever met.
Who was the first?
Andrew Fire. Yeah. So I just wanted to start with a question that I think a lot of people in the audience are probably wondering. What was it like to win the Nobel Prize, and where were you? Do they really call you at 4 o'clock in the morning?
Well, yes. If you live in California, they call you at 4 in the morning. And yes, I was asleep. But it wasn't as though it was a huge surprise. And I think it's true for most people who've won the Nobel Prize. They've won a bunch of other prizes. They've been told that they've been nominated, and maybe we shouldn't know that, but and you know the date when the prize is going to be announced. So it wasn't a total surprise. What was a surprise was the influence of receiving that award, and it turned me from being the leader of a group of 20 scientists, mainly trainees, into someone who got listened to and moreover was able to participate in the scientific enterprise by leading an organization like the NIH. Moreover, that medal is a very good shield against the anger of members of Congress or others in the administration. It's a very useful tool. It comes in handy, and I think that for me, the surprise was not the call in the middle of the night. The surprise was learning that that kind of distinction, and maybe that distinction only, catapults you into a realm where you may not deserve to be, but if you have the right intentions, you may be able to make good use of it.
So at the time that you were doing this research, did you have any idea that the discovery would really change the course of cancer research and cancer treatment far in the future?
Well, nobody knows the future, the present. That's one of the problems and excitements of life. I knew the questions were interesting, and I knew that the work we were doing was solid and worth pursuing, and there were more questions to come. And I could imagine ways in which the work we were doing might be influential, but reflect on what I said during my more program remarks, that it wasn't clear that discovering the precursor to the viral Sark gene was important until a lot of other people confirmed the work, not just by redoing our experiments, but by doing very similar experiments with other viruses that came not from, well, either from chickens or from mice or from monkeys, and showed that the general principle that the class of viruses, the retroviruses that carried cancer genes, had acquired them from normal genes, and even more importantly, that those genes were mutated in human cancer, and then showing that those mutations were clearly important because when you tried to interfere with the function of those mutated genes, the cancers went away, and sometimes in a very dramatic fashion. There's a phenomenon called oncogene addiction, in which interference with the function of these oncogenes will lead cells to undergo a process we call apoptosis, programmed cell death. And that's a very dramatic phenomenon. It shows you that if you had a way to interfere with the function of these genes in human cells, that cancers might disappear. And indeed, that does happen when you develop a drug that interferes, for example, with some of the enzymes that are made by mutant oncogenes. Cells die, and that's a great thing to have cancer cells die because it means they're gone and not just arrested. Those were all surprises, but surprises that proved to be, not simply pleasures, but also the very useful products of the science that the public supports.
So cancer is obviously a very complex disease, and oncogenes aren't the only genetic player, and there are many cancer mutations that we don't know yet, but we are making extreme progress right now in cancer research. Is there anything that you're excited about in the next 10 or 15 years that you think is going on in the cancer field that you want to share with us?
Well, I have to point out, first of all, that the work I talked about today is focused on oncogenes and the development of targeted therapy. But there are other developments in cancer research at the moment that are at least as exciting, if not more exciting. For example, the development of tools that allow us to arm the immune system to react more violently against cancers. For many, many years, even though it initially was assumed that cancers might be foreign in some nature and therefore rejected by the immune system, but efforts to demonstrate that the immune system would actually recognize a cancer proved to be of no avail. But about 15 years ago, my colleague Jim Allison was formerly at Berkeley, where Rick went to school, and then at Memorial Sloan Kettering, when I recruited him there, showed that he could make an antibody that would make the immune system active against cancers. And that was the first of several steps that have demonstrated that we can, in fact, engage the immune system in a powerful set of ways to confront cancers. Now, I think one of the great prospects in front of us is to find ways to combine immunotherapy and targeted therapy, possibly in some cases with traditional chemotherapy, which it should be remembered, still very, very effective in controlling cancers. I think the combinations of therapies, there are reasons that the combinations are often difficult to test in a coherent way, but when they can be done, my own prediction is that we'll get much better effectiveness. The other point is to reflect what we mean when we say a cancer is in remission. Daniel referred in his opening remarks to patients who had remissions, but sometimes those cancers come back because it's very difficult to know whether every cancer is eliminated. We have better and better tools, many based on the kinds of genomic work that Rick and his colleagues here are looking at, to judge just how many living cells are actually still in the body of an individual who doesn't have symptoms and doesn't have cancers that can be detected in the usual clinical tools. And being able to drive cancer down to a much lower cell number is going to be a way, I believe, that we will make remissions that really last and don't result in later recurrence of such tumors.
Let me ask a question. The idea of combined therapies that's been used in HIV, other viral diseases. You think that it seems that might allow you to reduce the doses of chemotherapy if you're still using it, because that's what's so harsh. Is that?
I think that's in the works. That's absolutely reasonable. I mean, the first line of reasoning here for doing combinations of approaches is to reduce what is the biggest problem with both immunotherapy and especially with targeted therapy, and that is resistance to therapy. Remember, the cancers arise because of our natural tendency to undergo genetic change and evolve. Cancers are evolutionary systems. Every cancer begins with a single cell that grows, and every time the cells grow, they undergo additional mutations, which will allow some cells to grow better than others and be selected for their increasing vitality compared to their neighbors. When you use an effective therapy, you kill many of those cells, but cells that acquire additional mutations that make them resistant to the therapy, such as a drug against an oncogenic protein, allow the evolutionary process to fuel a system of resistance against the drugs. If you have multiple kinds of therapies combined, the odds against actually developing resistance against all the multiple therapies becomes vanishingly low, as we've achieved in the treatment of HIV. And that same principle ought to be active in the world of cancer therapy. And it's just hard to design the kinds of tests that are effective. And then sometimes, quite frankly, it's hard for the drug companies to work together, put their therapies into the same tube, and because they're concerned that if patients don't do well, one company's product may be blamed as opposed to the other. So there needs to be some way that our regulatory process protects those companies from the kinds of penalties that might result from failures of combined therapy, so we can get the benefits of those combinations.
But I asked Sarah if I could ask another question of Harold. And actually, it's maybe the cancer docs in the room too. So when I was a kid, if a child got cancer, about 90% of them died. This was back in the 50s and 60s. And I think it's almost completely flipped. That's true, meaning
Depending on the cancer.
And maybe it's the type of cancer. Fortunately, childhood cancer is rare, relatively rare, but it still happens a lot. Is that true? And clearly, a lot of that has to do with research, figuring out how it works. But is there any? First of all, am I right about those numbers?
Yes, especially with the most common childhood cancers, childhood leukemias. We have the cure rate is very high, but it must be emphasized that we can't be satisfied with those numbers, because children who survive the kind of therapy that's required for treatment of childhood leukemia they suffer from the treatment. It's very rigorous. And the kinds of, and your point about developing therapies that are less toxic is very pertinent in that setting, where if we had more targeted therapies and immunotherapies, some of which are being developed, it's not as though we're ignoring pediatric cancers, simply sitting on our laurels, but there are still opportunities for improving the therapeutic approach. So the toxicities are less. There are fewer intellectual impairments as a result of rigorous therapy. There is a horizon there that we've not yet fully explored.
So I really liked your axiom during your presentation about choosing scientific questions that are going to have societal benefits. I mean, I think that should be an end goal of all scientists. But a lot of times, non-scientists don't understand how much work goes into the big discoveries that you're seeing in your life, like a drug, for example. Basic science research happens at places like HudsonAlpha, and that builds a foundation for things that become clinically applied. Rick, do you want to give one or two examples about how our research here at HudsonAlpha is helping the larger scientific community?
Yeah, and I think this is, I like to brag about this. We were lucky enough to be part of the Human Genome Project when it first started. Harold was, not immediately, but became a big supporter of it, especially when he was running.
I don't know why you don't say, why you say not immediately. I was
we were
on board right
you
from the
said
start.
so. No, I'm joking. It was one of the things that we learned from that was rapid free data release, even from day one. And so Harold has helped to lead this rapid release and free availability of data from journals and stuff, which is still a problem, but it's made big headway. So we came here because we had just finished, or a few years earlier had just finished, and we really wanted to see how do we take that information, like Harold was showing with the double helix, and actually learn what it means. And and we've done this we do this for cancer, we do it for brain diseases, we do it for sustainable agriculture, we do it because DNA is the genetic material for all organisms, or RNA for viruses, so that's been applied to many things, including being able to detect some diseases earlier by being able to do a blood test, by finding genes that Harold mentioned about how you get this resistance in cancer especially, but you get resistance because when you start to treat, you then select for cancer cells that have mutated to be resistant, and figuring out why that happens, and then try to figure out how to then go in and do something about that by figure out the genes that are responsible for that has been something that we've made real progress in. And we're not going to talk about agriculture tonight, but that's something that, and it's funny, that sounds like they're so different, but DNA is DNA. That's the way to think about it. So
I think you've raised a larger point about public expectation of what science is going to produce, and the frustrations people feel when they have diseases now that are not being prevented and treated. And I think that's a serious problem that can only be addressed by just trying to explain the realities of what it's like to try to study these incredibly difficult problems. I too feel frustrated that we don't treat pancreatic cancer very effectively. There are lots of cancers that we understand the genetic basis, but we don't have the tools. It's I think one of the issues we have not been successful in addressing in the most enlightened way is how to get people to understand that these are really tough problems that require lots of failures before we succeed. We now know that pancreatic cancer, to continue with that example, almost always driven by mutations in an oncogene called RAS. But it's only in the last 3 or 4 years that we've actually had a few drugs. They're not perfect, but they work reasonably well, and they're allowing some inroads. But drug resistance appears frequently. Some mutant forms of RAS are forms against which we don't have drugs. But on the other hand, 15 years ago, people said you couldn't make drugs against this protein, and that's clearly not true. So we've taken a couple of steps, but we have not taken all the steps required to reach the level of success that everybody hopes for. But it's not as though scientists have failed, we just haven't succeeded. and that is a difference. And I think whatever we can do here tonight to try to impress on you the fact that science has come a long way, but these are really rough problems, and new technologies, new understanding of chemistry are just as important in making advances against cancer or any other disease as doing another clinical trial with the things we already have and know.
So I just want to add to that, and Harold is, I know, is a huge proponent of this, involved in science policy, that a huge amount that we know comes from, I don't really like to use the word serendipity, but somebody studying something that they were interested in and having no idea that it would be practical. At his institution, recombinant DNA was, and at Stanford together, recombinant DNA, the ability to clone genes, was from a basic science problem that people were trying to solve. This wonderful technology called CRISPR now that allows you to edit genes in an incredible way was a basic science problem. So we, at HudsonAlpha, and I think Harold knows this, we've talked some about what we do, when Jim Hudson and Lonnie McMillan wanted us to come start a nonprofit research institute, the idea was to be a balance between the two. So we have all of our biotech companies that do practical and then applications of it, but even in our research, we do a combination of basic and applied. And partly, I think that the danger, and I remember this was a big deal when Harold was head of NIH. Yes, the applied stuff is really, really important. So we're not shunning it at all, but don't turn off the other part because you'll quickly lose the basic. If we're going to make biomarkers to discover, to actually predict disease or drug response or things like that, we better understand what those biomarkers are, for instance. There are many, everything we do relies on that.
So as a scientist turned science communicator myself, one of my big missions is to make science information accessible and understandable to everyone. And I think everyone in the room clearly wants to know a little bit about science, or you wouldn't be here. I think we're in a time where that is going to be more important than ever, that we're getting out accurate messaging. Is there any advice the two of you have to people for making sure they're getting science information from a reliable source?
Well, I think one of the things that is incredibly important and undervalued in the United States is teaching children at an early age how to talk the language of science. And that'll only happen when we have teachers in schools who understand the principles of science, and that's only going to happen when we pay teachers more. So there's nothing more important than doing that. The other place where I think education can be given to virtually everybody is through the press, and through that the press no longer means a newspaper. It means having people who understand science describe it, illustrate it in important ways on the web, on television, on social media, and we need people who are skilled at doing that, and whatever you can do to promote the wider dissemination of understandable science with its difficulties as well as its successes, the sooner we'll have a population that understands that science is tough business. People who do it are running an uphill battle that we need to try to understand rather than blame for failure to produce the results that they want quickly.
So as we're wrapping up tonight, do either of you have any last tidbits of information you would like to leave our audience with?
Tidbits? I don't think so. I'd welcome some questions from the floor if anybody has a question, because
Be careful about that, only a couple.
Yeah, a couple, and please, we're not providing medical advice tonight, so, but questions about what we've discussed here, my mind would be a welcome way for me to feel I've had contact with the audience.
Holler, please.
Repeat the question,
I will. May I answer? So why is it that she has worked with ALS? Why is it that neurodegenerative disease research seems slower than for cancer? And it's absolutely true. And there are a lot of, first of all, but it's changing a lot. The brain's the hardest thing in the world to understand. I think that is part of it. Alzheimer's research, I can't remember, Harold, the numbers, but Nick Cochran, who was one of our faculty, is a real expert on this, has shown the numbers. The amount of research money, not just NIH, but others going into Alzheimer's being the biggest of those, has gone up about 20-fold in the past 10, 15 years. So some of it, and it's not blaming anybody, it was partly where do we go from here. The tools that he talked about, not just genomics, but imaging, one thing after another, the adult stem cell stuff, meaning the CRISPR stuff that we all do, that's speeding things up a lot. It's still going to be hard. There's no overnight panacea for anything, but from my point of view, being in that field myself, that's what I work on. Where there is so much more going on and more knowledge now than there was 10 years ago. I've been working on this for 40 years, actually.
I think it's also worth reflecting on the fact that you could have posed the same question about cancer research 50 years ago. Yeah. And once you start to make some inroads, get some ideas that seem compelling and fresh, these are all difficult problems, but once you get a handle on the problem, which I think in the cases of most degenerative neurological diseases, we haven't gotten. In a few cases, like Huntington's disease, we know what the mutation is, but it's still very hard to counter the effects. And as Rick has pointed out, the brain is just an incredibly difficult organ to try to study and repair.
So, if you don't mind, I'm going to call you and then you, and I think we may have to. We have
That's
only
fine.
3 or 4 minutes. Yeah. So, loudly, please.
Let me just say a couple of things about that. I think certainly in the cancer field, the first large survey of all the irregularities in the genomes of cancers of many different types, and they are all very different, were collected from samples that were determined from samples that have been collected over many years, and 80% of those roughly were of in patients of European origin. We recognize that's a problem, and at the moment, there are many initiatives underway, a few of which I've been personally involved with, to try to increase the number of cancer genomes being analyzed that come from patients of color. The male-female balance has been pretty equitable over the years, but the most dramatic difficulty has been having more samples from patients of Asian and European origins. Asian and African and South American origins. And we're learning a lot from doing that. So I think there's no lack of incentive, just a matter of having enough scientists, enough financing, because this is still pretty expensive stuff. But we're going to learn a lot, and I think it'll be very helpful. So the commitment to equity on these issues has risen dramatically in the last 10 or 20 years. But the point you're raising is a very important one, and I'm glad you brought it up.
Thank you, sir. You made a statement that all cancers arise from a single cell, which I will admit sounds logical, reasonable, easy. And that alone makes me go, is this an assumption, or do we actually have sufficient knowledge to convince us unequivocally that it really is a single cell, or could it be another mechanism such as the interaction between partially two candidate cells? I don't know.
That's a very good question. There is a lot of evidence to support what I said. First, being that every time a cell divides, even the initial fertilized egg, mutations occur. So it's not as though mutations are rare; they occur at quite a high frequency. Second point is that it's now possible to generate evolutionary trees of an individual cancer, in large part because it's now possible to look at the genome of individual cells in a cancer and to look at the constellation of mutations in each cell and try to track the lineage. In fact, it's gotten so good, we know so much about how mutations are caused that you can actually set up an evolutionary tree in which you say, this mutation is caused by some lousy enzyme in the cell. This mutation is caused by exposure to UV irradiation. This is caused by exposure to cigarette smoke. So it is possible to make a tree that shows you that a cancer which is now spread throughout a patient's body and has many metastases, the mutational profile, we call the genotype, in these individual outposts of cancer cells in a patient look different, but there are commonalities. When you trace those commonalities back, while you can't, in retrospect, say there's only one cell in the cancer from which this is the origin, you can make that conclusion, you can draw that conclusion with a pretty high degree of confidence.
All right, we have to, we're over time, so I'm sorry, we need to stop, and I think we have one more person who needs to say something.
Okay, you mentioned the research being done with pancreatic cancer and how it is just baffling us, I guess, as lay people. I want to know specifically, if you can, tell me where we are in that battle and how long, I mean, I know we can't predict the future, but how long it might be or where we are, you know, borderline to a cure or some medications that can help with that disease. I had a brother who died last year at 49 years old of pancreatic cancer, and it has rocked my world, and it made me want to know more about cancer.
Well, first of all, very sorry for your loss. We know the major driver of pancreatic cancer in almost all cases is mutations in a gene called RAS. We have some drugs against those mutant proteins. Drugs are far from perfect, and when they have a beneficial effect, that effect usually doesn't last very long. There are efforts to try to develop immunotherapies. There are efforts to try to reduce the incidence of advanced stage pancreatic cancer by using some information we have that might denote risk factors for the disease and detect it earlier. One of the reasons pancreatic cancer is so difficult to treat is because it's commonly discovered in late stage and no longer susceptible to surgery. Some patients now and in the past have been cured, very few, but some with surgery when it's carried out at an early stage. Very difficult to make the prediction of when things will be better. It would be nice to have a drug that's more effective. We'd like to have multiple drugs. There are other mutations in pancreatic cancers that could be targets for new drugs. Drug combinations, in my view, would be better, as I tried to explain earlier. There is an effort to try to improve immunotherapies against pancreatic cancers. There have been some marginal successes, but again, this is, in my view, we're still in pretty early stages of trying to do this. So I can't give you clear answers. If I could, the whole world would be moving a lot faster. Yeah, I'd like to have it, but we don't have it. But there are reasons to feel we've made progress in understanding the disease, and I view that as one step towards making life better for patients with this terrible disease.
I want to just reiterate early detection. We're working on that. A lot of people are working on it. Blood tests or something. Early detection for probably any disease gives you a chance to hit it faster and earlier, as Harold just mentioned. Yeah.
Thank you so much to Dr. Varmus for visiting. I'm just going to invite Danny back to the stage to close us out tonight.
Thanks, Sarah. Everyone's awake now, I hope. As a 28-year leukemia survivor, I am incredibly grateful for the men and women who have worked to advance our understanding of cancer, as well as those working to develop new and novel therapies. Dr. Varmus, Dr. Schroeder, thank you again for being here tonight and for your contributions to the field of cancer and to cancer treatment. Dr. Myers and Dr. Sharman, thanks for making a very engaging, entertaining evening. It certainly brightened up what is otherwise a very dreary evening out there tonight. As we head into the holiday season, many of us are reflecting on the things that we're grateful for, maybe making plans to support year-end giving for causes that we find near and dear. I'd like to encourage you to add HudsonAlpha to that list so that we can help to advance the scientific understanding and the work of our scientists here at the Institute. On the screen behind me is a QR code that will take you to our online giving page. There's also information about how you can give to HudsonAlpha in the informational material that you received coming in the door. Additionally, members of our advancement team will be around after this event if you would like to learn more about what happens at the Institute, get signed up for our mailing list, sign up for a tour of the Institute. They will be happy to help you. I know there are many of you in this room who have supported HudsonAlpha already this year, and I just want to say thank you. We are extremely grateful for all the work that you do to support what goes on here on the campus. This may have been the last event of 2024, but we're already busy scheduling a whole series of events for 2025 to help you stay connected with what's going on here on the Institute campus. In January, you'll receive an email, if you are signed up to our email distribution, with dates of those events. I hope that you will put them on your calendar and plan to join us. In closing, I want to thank all of you for being here tonight. I want to thank you for being a friend and a supporter of HudsonAlpha. And I want to wish you a safe and happy holiday season. Safe travels on your way home tonight. Good night.